The Geologic History of Iowa, produced by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association. The Precambrian Eon, from 4,600 to 2,500 million years ago. The Earth's surface solidified about 4,600 million years ago. That's 4.6 billion years ago. To better understand and discuss this huge period of time, geologists have subdivided it into many small blocks and given them names. By far the largest of these blocks of geologic time is called the Precambrian Eon, which includes the first 4,100 million years, or 88.7% of the Earth's history. From drilling in Iowa, Precambrian rocks of these ages have been identified. North America was assembled from a number of smaller pieces over geologic time. The Precambrian core of the continent is called the North American Craton. The earliest of these cratonic fragments are Archean age, shown in red, with the oldest being over 4 billion years old. During the Proterozoic, between about 2,500 and 520 million years ago, these fragments colored blue were added. Iowa, in the center of the craton, is primarily underlain by Proterozoic rocks, with older Archean age rocks restricted to the northwest corner of the state. This map provides a little closer look at the geology of Iowa and the states to the north. Precambrian rocks are exposed, or as geologists say, outcrop, in the northern parts of Minnesota and Wisconsin, an area referred to as the Precambrian outcrop belt. In the southern areas of those states, and almost all of Iowa, Precambrian age rocks are buried beneath younger sedimentary rocks. This area of buried Precambrian rocks is called the Precambrian subcrop belt. The only place that Precambrian rocks are exposed in Iowa is the very northwest corner. This is our most modern map of the geology of the Precambrian rocks of Iowa and the surrounding area. The red line shows a dividing line between the older Precambrian Archean rocks to the north and the younger Proterozoic rocks to the south. Iowa's oldest known rocks were encountered in a series of drill cores from northeast Sioux and southeast Lyon counties. These rocks include the Otter Creek mafic complex that has been dated at 2,710 million years. However, another rock unit encountered in the drilling, the Matlock Banded Iron Formation, is probably older, although it has not been dated. The other Iowa Archean rock unit encountered in drilling is the Lyon County gneiss, colored yellow-brown on the Precambrian geologic map. It has been dated at 2,523 million years old. A gneiss is a metamorphic rock that has been heated and deformed by tectonic forces after it was originally formed. The Morton gneiss is a similar Archean rock found a few tens of miles to the north in Minnesota. About 2,500 million years ago, the last era of the Precambrian began, the Proterozoic. Large areas of land were added to the southern edge of the North American Craton during the Proterozoic, including most of Iowa. During a period called the Yavapai Orogeny, between about 1,800 and 1,700 million years ago, the largest portion of the state, shown in blue on this map, was attached to the older Archean cratonic rocks, shown in red. About 100 million years later, or about 1,600 million years ago, a second larger suite of rocks, including the southeastmost part of Iowa, was attached to the Yavapai rocks on the southern edge of North America. These rocks, colored pink with stripes, were in place during a period called the Matsutzal orogeny. An orogeny is a process that includes the collision of large masses of crust that creates and deforms rocks and welds crustal pieces together. These crustal masses are fragmented pieces of the Earth's crust called plates, and the process that moves the plates is called plate tectonics. So these Proterozoic additions to the North American Craton demonstrate that the Earth had cooled enough to allow the beginning of plate tectonics. But just what is plate tectonics and how does it work? Let's start out by looking at the composition of the Earth's outer layer, its crust. The crust is composed of two principal components, oceanic crust and continental crust. Oceanic crust is mostly dense black iron and magnesium-rich volcanic rocks, dominantly basalt. These are the rocks that are commonly seen in Hawaii and other volcanic islands. The continental crust is composed of lighter silica and aluminum-rich igneous rocks, dominantly granites, such as this exposure at Stone Mountain, Georgia. The crust is broken into a series of large and small crustal plates that allow mantle heat to escape at their boundaries. Most of these plates include both oceanic and continental crustal material. Oceanic crust is relatively thin, averaging only about 6 miles in thickness and reaching a maximum thickness of about 12 miles. The thicker continental crust averages about 27 miles in thickness and reaches a maximum of about 45 miles. As mentioned earlier, oceanic crust is denser, averaging about 3 grams per cubic centimeter as compared to continental crust's average of about 2.7 grams per cubic centimeter. As the ocean crust gets older, it continues to thicken as mantle material is added to its base. Eventually, the ocean crust breaks free from the continental crust and sinks into the mantle, a process called subduction. The zone of subduction marks the edge of a continental plate. Ocean crust that is lost to subduction is replaced by new crust that forms when magma from the mantle moves up into the spreading centers. Here's another map with the Earth's tectonic plates outlined in red. Each of the plates is moving in the direction shown by the arrows. The length of each arrow indicates the relative speed that the plate is moving. The plates with the longer arrows are moving faster. The average speed of plate movement is about 1 centimeter per year, about the speed that your fingernails grow. But how is it that plates with no spaces between them can be moving in different directions and at different speeds? In order to allow this variability of plate movement direction and speed, they interact with one another in three principal ways. The first is when two plates are moving away from one another. This is called divergence, and it usually happens beneath an ocean. The areas where divergence is occurring are called spreading centers because the plates are growing and spreading away from one another along these zones. Material that is moving upward from the mantle becomes a part of the ocean crust. The blue lines show the divergent plate boundaries. An example of a divergent plate boundary is the Mid-Atlantic Ridge. Another way that plates interact with one another is where they're crashing together, called convergence. The red lines show the plates that are converging. Plates can converge along zones where the ocean crust of one plate is subducting below the ocean crust of another plate. This is called ocean-ocean subduction. The oceanic crust of one plate can subduct beneath the continental crust of another plate. This is called ocean-continent subduction. Or the continental crust of one plate can crash into the continental crust of another plate, a process called continent-continent collision. In this case, only the denser lower portion of the crust, or the lithosphere, is subducted into the mantle. The lighter continental crust is too light to be subducted, so it just piles up at the zone of collision. An example of a continent-continent collision is the zone where the Indian plate is colliding with the Eurasian plate, and the continental pileup is called the Tibetan Plateau and the Himalayan mountains. The third type of plate interaction is called strike-slip. This is when one plate is sliding sideways past another plate. The zone of strike-slip plate interaction are shown by light green lines on the map. An example of this is the interaction between the North American plate and the Pacific plate in California, where the zone that they are sliding past one another is called the San Andreas Fault Zone. Plate tectonics during the Precambrian worked in much the same way, but because of higher heat flow, the plates probably moved a little faster. Sometimes multiple arcs can form, with some plates subducting under pieces of ocean crust to form volcanic island arcs, while others slide below continental crust, producing volcanoes many miles inland from the subduction zone. This is what happened in Iowa during the Yavapai Orogeny, when Yavapai age volcanoes erupted within the older Archean rocks of the North American craton to the north, while island arcs were being formed in the oceans to the south, later to be driven up against the existing craton. In Iowa, these Yavapai rocks are called the Camp Quest gneiss. They form the basement of a large portion of Iowa, shown in light blue between the dashed yellow lines on the Precambrian geologic map of Iowa. They are named from a core drilled by the Iowa Geological Survey in 1979 near Lamars in Plymouth County. Here's a photo of some of the Camp Quest gneiss. You can see the banded nature of the minerals in the rock that define it as a gneiss. Minerals at the top of the core, like those in the first row on the left, have been weathered to clays, producing the whitish coloration. In 1987, an attempt was made to determine the age of these rocks, but because of contamination within the samples, an accurate age could not be determined. Yavapai rocks were also encountered in drilling in the Manson impact structure, an old meteor crater in Pocahontas and Calhoun counties. These rocks were uplifted thousands of feet on the central peak of the impact structure and were encountered only a few hundred feet below the land surface. The Manson Yavapai rocks were dated by the University of Kansas in 2007 and produced an age of about 1,705 million years. The date is not very precise, having an error range of plus or minus 30 million years, probably as a result of the partial disruption of the age dating system by the energy of the impacting meteorite. After cessation of major volcanic activity associated with the welding of the Yavapai rocks to the North American craton and a short period of regional erosion, the last gasp of volcanic activity occurred along the southern edge of the continent. Melted granite crust erupted as volcanoes on the surface of what is now northwest Iowa. If we take a closer look at the Precambrian geologic map in this area, we can see these rocks colored blue, mostly buried by the younger pink rocks. These volcanic rocks, called the Hull Rhyolite, were encountered in two core holes in southeast Lyon County and dated at 1,782 million years. Examination of the cores revealed that some of the Hull Rhyolite was deposited as a molten magma flow, while others were deposited as volcanic ash. This tells us that the volcanoes from which the Hull Rhyolite erupted were somewhere nearby. After the eruption of the Hull Rhyolite and related rocks, North America underwent a long period of weathering, with rocks being deeply eroded and converted to quartz sand and clay minerals. Rivers carried these sediments to the seas, and alongshore currents distributed the sand and other sediments extensively along the continental margin, not just in the United States, but in numerous areas around the North American continent. This period of time, around 1,650 million years ago, is called the Baraboo Interval, named for the quartz-rich rocks found in Baraboo, Wisconsin. Most of this sand was ultimately eroded away, but remnants of this great sand sheet were cemented by quartz to form a rock called quartzite and preserved in numerous locations from Arizona to Wisconsin. These rocks have been assigned many local names, but those preserved in northwest Iowa and adjacent areas of South Dakota, Nebraska, and Minnesota are known as the Sioux Quartzite. Although the Sioux Quartzite is present in most of Lyon and portions of Sioux, Osceola, and O'Brien counties, younger rocks and sediment obscure it virtually everywhere in Iowa. The best place to see exposures of Sioux Quartzite in Iowa is at Gitche-Manitou State Preserve in the very northwest corner of the state. This oblique Google Earth photo shows the northwestmost exposure of the Sioux Quartzite in Iowa at Gitche-Manitou State Preserve, outlined by the orange dashed line. The yellow dashed line identifies a border between Iowa and South Dakota. The dark area in the center of the preserve is water in an old quarry where the Sioux Quartzite was mined in the late 1800s. The light-colored areas to the west and east of the quarry are exposures of Sioux Quartzite. This is what the quarry looks like on the ground. The quartzite is pink, with surface moss and lichens giving some areas a dark gray appearance. The white area shows where calcium carbonate was deposited when water levels in the quarry was higher. A surface exposure of the Sioux Quartzite displays its characteristic pink color. It has been fractured and ground flat by the passing of numerous glacial ice sheets and has been polished by centuries of wind-blown dust. The Sioux Quartzite has been mined for building materials in the past in Minnesota and South Dakota. This building, constructed of Sioux Quartzite, is the Pipestone County Museum in the town of Pipestone, Minnesota. The Sioux Quartzite is still quarried in Minnesota and South Dakota for use as ballast along railroad tracks and for aggregate that is used in road construction, giving the roads of northwest Iowa and the surrounding area a pinkish hue. A few hundred million years after the deposition of the Sioux Quartzite, the Makanda Orogeny created a swath of island arcs, shown in striped pink on this map, which collided with and were plastered to the southern edge of the North American craton. The fourth of these colliding Makanda island arcs deformed the relatively young Yavapai crust and the rocks on it. Sioux Quartzite rocks were tipped and bent in several areas, including a quarry at New Ulm, Minnesota. This photo shows the dip of once flat-lying Sioux Quartzite at the southern edge of that quarry. By about 1600 million years ago, most of the continents on Earth had joined together to form one of the first supercontinents, called Columbia. Iowa was located near the center of the southern margin of this huge land mass, in an area of recently formed continental crust. This set the stage for the next episode in the Precambrian geologic history of the state. The creation of a supercontinent blocked the natural heat flowing from the mantle from reaching the crustal surface and led to the melting of lower crustal rocks. Magmas created by this melting gathered in large pools of molten rock called plutons or batholiths. Some magma was forced into cracks in the crustal rocks called dikes. Others were squeezed between horizontal layers of rock and called sills. These magmas cooled slowly, insulated by the surrounding rocks, and formed crystals of such minerals as feldspar and quartz. Since they were intruded into pre-existing rock, they are called intrusive rocks, most of which was granite. Sometimes a magma is forced to the surface, where it erupts as lava and forms volcanoes. Magma that is exposed to air cools much faster before crystals have time to form. Since these rocks were extruded from the earth, they're called extrusive rocks, mostly rhyolite. Rocks formed by this process of deep crustal melting are referred to as anorogenic granites and rhyolites because their formation was not a part of a continental collision or orogeny. Between about 1500 and 1300 million years ago, two major episodes of crustal melting affected the supercontinent of Columbia. The melting appears to have been limited to the younger, newly accreted Yavapai and Makanda crust. During these episodes, anorogenic granites and rhyolites were intruded and erupted over a wide swath of the southern edge of the continent, an area at least as large as the region colored yellow on this map. Later erosion removed much of the extrusive rock, but dated granites and plutons of this age are known from the location with yellow, blue, and red dots, and rhyolite remains over the area with the yellow tint. Although none of these anorogenic rocks can be seen at the surface in Iowa, there is a signature that is evident in this map showing variations in the Earth's magnetic field in the state. These granites and rhyolites have greater concentrations of the magnetic mineral magnetite than most crustal rocks. These magnetite grains interact with the Earth's normal magnetic field to produce anomalies that appear on the aeromagnetic map as subcircular areas of yellow, orange, or red. Most of the anomalies that appear in these areas were produced by the 1500 to 1300 million year old granitic intrusives. On the map of the Precambrian geology of Iowa and the surrounding area, these granite intrusives are shown as dark orange, and the rhyolites that were extruded at this time as a lighter orange in the southeast area of the map. The Iowa Geological Survey has age-dated cores from two of these granite plutons. In western Iowa, the Quimby core from southern Cherokee County was dated using uranium-lead techniques at 1433 million years by University of Kansas geologists. And in eastern Iowa, the Green Island core from Jackson County was dated at 1485 million years. The rubidium-strontium ages tell us the age of the crust that was melted to produce these granites. 1840 to 1830 million-year-old Yavapai crust. After the intensive period of anorogenic plutonic and volcanic activity, the Columbia supercontinent began to break up. As a part of this breakup, a widespread series of cracks developed in the crust and were filled with a magma from great depth. This magma cooled to form a series of black, iron-rich crystalline dikes. Two of these dike swarms are the Mackenzie dikes in northern Canada and the Sudbury dikes in eastern Canada. One of these dikes was also encountered in the basement surface in Carroll County, Iowa, during the drilling of the Amoco MG Eischeid deep petroleum test well in 1987. By about 1240 million years ago, the southern and eastern edges of North America had rifted and had moved away from the continent, and the Grenville Ocean had opened. It didn't take long for the continental fragments that once were the supercontinent of Columbia to reassemble to form the next supercontinent, Rodinia. This time Iowa ended up near the center of the supercontinent. The power of the continental fragments crushing into one another deformed and melded rocks and pushed up large mountain ranges. This belt of mountain ranges and deformed rocks is shown in orange on this map. As the Grenville Ocean closed, continental fragments that now comprise northern Europe, South America, and Africa smashed into the edges of North America about 1100 million years ago. This collision pushed up a range of mountains, the Grenville Mountains, that were comparable to today's Himalayan mountains. At the peak of that mountain building, a large rip occurred across the southern edge of the continent, the Midcontinent Rift System. Such a rift occurs when the continent is pulled apart and fractures, with magma from deep within the crust flowing upward through the cracks and pouring out onto the surface. The Midcontinent Rift extends from northern Ohio across Michigan, then runs the length of Lake Superior between Minnesota and Wisconsin, across Iowa and southeastern Nebraska, and into Kansas and Oklahoma. Magnetites in the basalt that filled the center of the Midcontinent Rift create a long, linear, positive magnetic anomaly, shown as orange on this aeromagnetic map. They are especially strong in the Lake Superior area and along the Minnesota-Wisconsin border, but become more muted as they become more deeply buried in Iowa. The Midcontinent Rift is even more pronounced on this map that shows variation in the Earth's gravity. The rift-filling basalts are much denser than the average crust, so they create a red-colored positive gravity anomaly on the map. The deep, low-density sand and clay-filled basins that flank the rift in Iowa and other regions create a blue-colored negative gravity anomaly. Using information from the study of exposures in the Lake Superior region, gravity and magnetic maps like those just shown, and very limited drill data, geologists have been able to map the geology of the Midcontinent Rift System. This generalized map shows the extrusive basalts associated with the rift in green and the flanking sand and clay basins in brown. 3 test wells have been drilled into the rocks of the Midcontinent Rift in order to learn more about them and to evaluate their petroleum potential. The first of these, the Texaco Porsche No. 1 well, was drilled in northern Kansas in 1984. The second, the MG Eischeid No. 1, was drilled in Carroll County, Iowa in 1987. And the final one, the Tara Patrick No. 7-22, was drilled in northwestern Wisconsin in 1992. In Iowa, a number of wells have been drilled into the rocks of the Midcontinent Rift System. Most of these are clustered in areas where subsurface structures have been developed for the storage of natural gas. Some wells were drilled as a part of petroleum exploration programs, and a few others were drilled as water wells. Information from these wells, supplemented with interpretations of magnetic, gravity, and other geophysical data, led to the development of this map of the rift through Iowa. The oldest rift rocks are volcanic and plutonic rocks, mostly basalts, shown in green. They are overlain by lower red clastic group, red shales, and sandstones, shown in yellow-brown, which is itself overlain by the upper red clastic group of sandstones and shale, colored light yellow. Only one of these Iowa wells penetrated deeply into the Midcontinent Rift rocks, the MG Eischeid No. 1 Deep Petroleum Test Well, drilled in Carroll County in 1987 by Avalon Explosion and shown as a yellow dot on this map. This is the drill rig that drilled the Eischeid well. It towered over 75 feet above the surrounding cornfields. And such a large rig was necessary because the hole that it drilled reached a total of 17,851 feet, almost 3.5 miles into the earth, penetrating totally through thick sequences of upper and lower red clastic groups. This is a lithologic log of the MG Eischeid No. 1 deep well. It was prepared by geologists to examine small chips of rocks that were washed out of the borehole and collected at regular depth intervals during the drilling of the well. The log describes the rock samples that were collected, that is, their lithology, and identifies the stratigraphic unit that they came from. The first 2,700 feet of the well penetrated Cenozoic, Mesozoic, and Paleozoic age rocks from units that are all exposed at the land surface in various regions of Iowa. Below that, it passed into Precambrian age rocks that are very poorly known, and most of which don't have formal stratigraphic names. The first of these Precambrian units, designated Unit H, was about 800 feet of fine to coarse-grained sandstone not directly associated with the Midcontinent Rift, but apparently deposited by a river that flowed across Iowa at some time between 1 million and 500,000 years ago. Below that, at a depth of about 3,600 feet, the drill passed into sandstones, siltstones, and shales of the upper red clastic group. Based on their characteristics, these rocks were subdivided into 3 informal units, F, G, and E, totaling about 6,900 feet in thickness. Below that, at about 10,500 feet, the drilling encountered the shales, siltstones, and sandstones of the lower red clastic group. 3 informal formations were also identified in this group, D, C, and B. Unit C contained thick sequences of black shale, potential petroleum source rock. About 7,200 feet of this lower red clastic group was penetrated in the Eischeid well before the drill encountered the pre-rift igneous rocks of the Iowa basement complex. Although most of the Eischeid well was drilled with the rock bit that chipped the rock into small pieces, at a few select depths, a core barrel was used to collect larger cylinders of rock for more detailed studies. Slabs cut from these cores provide an excellent opportunity to see what these deeply buried Midcontinent Rift rocks look like. A core from 8,837 feet in Unit F of the upper red clastic group shows a red-colored silty sandstone, the layering indicating deposition by a river. A core from 11,390 feet in Unit D of the lower red clastic group is a red silty shale with multiple cross-bedding features, suggesting shifting currents in a shallow, slow-moving river. Samples of thin-layered black silty shale from 15,096 and 97 feet down in Unit C shows deposition in a lake with heavy accumulation of organic material from the single and multicell animals that lived in the lake. This organic material altered the chemistry of the water at the bottom of the lake, allowing pyrite, that's iron sulfide, to crystallize. Pyrite is the gold-colored mineral seen in the lower sample. Much of the original organic material could have been converted to oil and gas. A core from a little deeper in Unit C, from 16,045 feet, shows the same layered black shale and gray siltstone, except these layers have been deformed and tilted. The rock would have been in this orientation in the borehole when it was recovered. This deformation identifies a period of structural movements in the Midcontinent Rift. The Iowa Geological Survey also has a few short cores of Midcontinent Rift volcanic and plutonic rocks that show us what these igneous rocks looked like. 2 examples of these cores are a basalt from the Sharp No. 2 well in Webster County and a gabbro from the Finnegan No. 1 core in Guthrie County. The sharp basalt is an extrusive rock erupted from a volcano or a fissure. When the magma is in the earth, it is under pressure that keeps gases dissolved, much like a capped bottle of soda. When the magma is erupted, the pressure is released and the gases come out and rise to the top of the flow, much like bubbles erupt to the surface when a soda is opened. When the magma cools and solidified, these bubbles are trapped near the flow top. Here's a photo of Midcontinent Drift Basalts from near Lake Superior. The holes, called vesicles, left from these bubbles are evident in the top of this basalt flow. However, if the basalts are then deeply buried, the vesicles can be filled with secondary minerals. This happened to the sharp basalt, and the vesicles were filled with green epidote and white calcite. The Finnegan Gabbro is an intrusive rock, so it cooled slowly enough that the magma crystallized. The crystals give this rock a mottled appearance to both the rounded outside surface on top and the cut slab below. If we look closely at the polished surface, we can see that these crystals are plagioclase feldspar. These crystals are the light-colored areas on the rock. Modeling of the gravity and other geophysical data has allowed geologists to interpret the geometry of the Midcontinent Drift as it passes deeper into the crust. If we make a cut through the crust across the rift and look at the cross-section, we can get an idea on how this rift formed. The crust split open and layers of volcanic and plutonic rocks filled the crack. Then, deep basins developed on the flanks of the feature and filled with river and lake deposited clastic sedimentary rocks. A few sedimentary basins also formed on top of the rift volcanics, but most of them have been eroded away. With information from this and many other cross sections, a 3D model of the rift in Iowa can be constructed. This is a view of one of those models. Looking over the land surface from west to east, you can see Iowa outlined in white. The Midcontinent Rift extends all the way down to the base of the crust, about 24 miles down. This illustration shows rocks from two periods of volcanic and plutonic activity, an older green period and a younger blue period. The lower red clastic rocks are orange on this illustration, and the upper red clastic rocks yellow. The pink area is the face of a north-south fault that was discovered during the modeling. There is one other group of rocks in Iowa that are associated with the Midcontinent Rift. These are a series of intrusive rocks shown mapped in dark green in northeast Iowa and called the Northeast Iowa Igneous Complex. These rocks are currently being investigated by the U.S. Geological Survey geologists who think they might be rich in platinum, gold, titanium, and other valuable elements. They may eventually be the targets for underground mining. This completes our brief review of what is known of the Precambrian rocks in Iowa, but a series of events late in the Precambrian that didn't leave a known rock record in the state were very important to all of us. Between about 780 and 630 million years ago, the Earth apparently endured three periods of time when the entire surface of the planet was frozen over, periods known as Snowball Earth. These periods apparently began when all of the Earth's continents were aligned on or near the equator. Chemical reactions associated with the equatorial weathering of the rocks on these continents began to remove carbon dioxide from the atmosphere, until it's estimated that CO2 levels had dropped to about 1/1000th of 1%. CO2 in the atmosphere currently constitutes about 4/100ths of 1%. The low levels of CO2 produced a reverse greenhouse effect, with heat rapidly escaping from the Earth and temperatures dropping dramatically. It's believed that the temperature eventually fell to a planet average of about 40 degrees below zero. All of the Earth's oceans were soon covered by ice, and most of the land areas blanketed by a layer of snow. The ice and the snow that blanketed much of the land then dramatically reduced the weathering of these rocks, and with the help of volcanic gases, the CO2 level began to increase, again dramatically, perhaps to values of about 10% of the Earth's atmospheric gases. This created a super greenhouse effect, and temperatures quickly rose to an estimated Earth average of about 120 degrees, which of course melted all the ice and snow, and the rock weathering began again. It is thought that this cycle occurred three times until the continents had moved sufficiently to return the Earth to a more normal climate. That's an interesting story, but why is it so important to us? These three periods of snowball Earth are shown as three blue bars on this timescale. Note that the right side of the timescale has been greatly expanded so that each of the individual snowball Earth events is visible. If we superimpose the evolution of life forms on this timescale, we see that bacteria and archaea first appeared on Earth about 3,500 million years ago, and they continued to expand through the Precambrian to the beginning of the Paleozoic about 542 million years ago. About 2 billion years ago, eukaryotes, those are forms whose cells contain a nucleus, like those in our body, first appeared and slowly evolved into filamentous algae and unicellular protozoans. Then, between about 575 and 520 million years ago, right after the Snowball Earth episodes, the eukaryotes suddenly began to evolve rapidly into a wide variety of unusual animals. This period of rapid evolution is known as the Avalon Explosion and continued into the early Paleozoic Cambrian period, where it's called the Cambrian Explosion. Within the last 33 million years of the Precambrian and the first 22 million years of the Cambrian, most of the major lineages of animals on Earth today suddenly appeared. And many geologists believe that the Snowball Earth events were responsible for this evolution of life forms. By increasing the level of nutrients in the oceans, they triggered this rapid evolution. This completes our review of the Precambrian Eon of the geologic history of Iowa. It was prepared by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association.